So see here the graph, whatever we have seen. So this is going to be VDS versus ID. The maximum drain current is got when VGS equal to 0. This is your non-saturation region and this is your saturation region. Saturation region, the current becomes constant. This is your linear region where you can use MOSFET as your amplifier. This is the region where you will use your JFET or MOSFET as your switch. Saturation, now the device is turned on. The device is in on state. As you increase the gate source voltage in negative sense, you can see the drain current starts reducing. So at -1, see here it is close 20 milliamps, it has become 12 milliamps. -2, it has become 6 milliamps. -3, it has become 2 milliamps. So at one particular voltage, when VGS equal to VP, when the VGS is equal to the pinch off voltage VP, the drain current will be completely becoming 0. So for one particular drain current, you see the ID will become completely 0. That is going to be the pinch off voltage. And saturation region now, the current becomes constant. Non-saturation region now, there is linear increase in the ID with respect to your VDS. So ID will be proportionate to VDS. So here you see it is almost linearly increasing. All the drain currents will linearly increase before attaining saturation for a particular value of VGS. So if you find the voltage graph, you can draw the voltage graph VDS at. If you plot VDS at VP naught minus VBI plus VGS. VP naught is pinch off voltage, VBI is the built-in potential, and VGS is what the extra voltage you apply at the gate source terminal. So if you apply that, if you plot the voltage graph for VDS, you get this voltage graph is increasing because it is increasing. It is a linear graph, right? So it will increase linearly with respect to the applied voltage. So this ideal saturation current is now independent of drain to source voltage. So in a good approximation only, what we see, you cannot remember this equation fully. It consists of so many terms. So good approximation, what we do a good approximation to the drain current and we get the drain current equation as this one. ID is equal to IDSS into 1 minus VGS by VP the whole square. Why we have done this approximation means if you measure current using this equation, or if you measure the drain current using the previous exact equation, the difference is going to be very, very less. The difference is very, very minimum. That is why they say that even the approximate model can be used for modeling your JFET. It is not going to be that much, it is not going to contain that much amount of error. And you know, in this ID equal to IDS into 1 minus VGS by VP the whole square equation, ID is your drain current. This is your saturation current. VGS, you know, it is the gate source voltage, whatever you are going to apply. And VP is the pinch off voltage. The maximum current is got when VGS equal to 0. And 0 current is got when VGS equal to VP. So from this approximate graph, we can draw the transfer characteristics for N channel and P channel JFET. See, this is the N channel, P channel JFET. So as you increase the VGS, the drain current is reducing. So this is your ideal curve, the straight one. And approximate curve is in dotted line. You see the difference is very, very minimum. So that is the reason why they have approximated and given us this equation. Otherwise, we would be using this big equation everywhere in all our calculations. The ரெண்டுத்துக்கும் difference வந்து ரொம்ப கம்மியா இருக்கிறதுனால, see here, the difference is very, very minimum between the actual curve and the approximation curve. That is the reason why they are saying you can use the approximate equation itself for all the analysis of your JFET. You need not consider the ideal equation all the time, since the difference is very, very meager. Okay, and so the ideal current characteristics is given by here. So this is the curve what we have. This is the equation what we have seen. So this threshold voltage, yesterday we have seen what is threshold voltage. The threshold voltage is the voltage above which the device is turned on or turned off. The threshold voltage is given by Vt equal to Vbi minus Vpo. So Bi is your built-in potential and Vp naught is your pinch-off voltage. For N channel, threshold voltage is negative. For N channel depletion MOSFET, threshold voltage is negative. And for enhancement MOSFET, threshold voltage is positive. Okay, so if VT is greater than 0, for enhancement MOSFET, you can say VBI is greater than VP naught. So pinch off voltage is always less than the built-in voltage, and for depletion MOSFET, it is the other way around. VT is less than 0, right? So VBI will be less than VP naught. So the built-in potential will be less than the pinch off voltage. So the design of enhancement MOSFET implies the use of narrow channel thickness and low channel doping concentration to achieve this. So you know that built-in potential is playing a major role in the design of MOSFET, JFET and MOSFET, because you have a depletion region present inside. So that has to be taken into account. So the threshold voltage VT is given by VT is equal to VBA minus VP naught. So if I rearrange, I can write VBA equal to VT plus VP naught. So if you are going to go for enhancement JFET, you have to use narrow channel thickness and low doping concentration to achieve the condition VT greater than 0. If you are going to go for depletion MOSFET, suitably you have to change the design of your circuit to achieve the condition VT going to be less than 0. So all these are theoretical support, and these will be considered during fabrication process of your devices. So when you are going to fabricate ICs of JFET or MOSFET, all these considerations will be put into effect. And the final simplified answer, the saturation expression for saturation current is given. So the saturation current finally ID1 sat equal to mu epsilon W by 2AL. Then saturation happens after threshold. Once threshold voltage is reached, the device is driven into saturation. So saturation current value approximately is given by mu n epsilon W by 2AL. So you see it is independent of voltage. So it is a constant term. Mu is the mobility of electron, epsilon is the permittivity, W is channel width, A is your channel height, L is your channel length, right? So even in the graph we have seen, right? So after a pinch off, the current becomes constant. Current will not depend on VDS. அதே தான் இந்த equation பாருங்க. There is no term involving voltage in the saturation drain current equation. The current is going to be constant term for voltages above the threshold voltage VT. When you apply any voltage after VT, the device is going to behave like a constant current source. The current is going to be constant. So in saturation, I can write the expression for drain current as Kn into VGS minus VT the whole square. Kn is going to be the conduction parameter. This equation only we have seen in channel modulation. If you remember, the same equation we have seen in effect of channel modulation, the same thing is derived now. Kn is called as the conduction parameter, and this equation you can see. So when you apply any voltage more than VT, this ID will become constant. Constant drain current will be flowing through your device after you turn on or turn off. Turn off means the current is 0. When you turn on your device after the pinch off voltage, this constant current or saturation current will be flowing through your device. And the Kn is called as the conduction parameter, which is completely a constant. And that VGS minus VT is also going to be constant. So it is going to be constant voltage. So you can see from the equation, above the threshold voltage, the conduction current or the drain current is constant, which is called as the saturation drain current of your device. Okay, so today's class was exclusively dedicated for learning about the exact current equation of JFET. So we have seen what is the approximate current equation, what we have been using. This is called a Shockley's equation, and we have seen that MOSFET is a square law device. The current is proportional to voltage square. So this equation is okay, but you have something called as the exact current equation of JFET. So we have to know how to derive that exact current equation of JFET also. So we have done that. Started with the resistance value, resistance of channel. Then slowly we have found out the current. From current, I'll be finding out from voltage, I'll be finding out the current. And if I integrate the expression for current, I'll be getting the ID1 drain current. By substituting the potential depletion layer with H1 and H2, I'll get exactly the equation for ID1. And from ID1, after drawing the current equation for ID1 and the exact approximate model, I find that there is no difference. Both the currents are going to be approximately same with very little difference. So they suggest that So you need not use the ideal characteristic curve always. Also, the equations look very, very big, right? So it is enough if you see if you use the approximation curve in the for all your studies, because difference is going to be very, very minimum. And having understood this, I have derived what is the expression for saturation drain current in JFET. So it is going to be Kn into VGS minus VT the whole square. Kn is going to be called as the conduction parameter, and VGS minus VT, it is going to be the difference in the applied gate source voltage and the threshold voltage of your MOSFET. What is the threshold voltage? It is the voltage, it is the minimum voltage which is required to change the state of your device. Maybe if the device is in off state, how to turn it on. The device is in on state, how to turn it off. So it refers to the minimum voltage for turning on or turning off your device. So any doubt anybody is having in today's class, you can ask it.